Swayam Prabha. Digital India. Educated India.
So, last class I have discussed that simplified procedure that is proposed by Seed and Idris in 1971, and then we discussed how we will get the shear stress developed during an earthquake. Okay. Now, today I will discuss one example problem, and then I will show you how we will use those developed equation to check whether in the soil the liquefaction will occur or not. Okay. So, we have done a test and we have collected the soil sample at different depth, because this is a lab test. We are now discussing about the lab procedure. So, that here we will get that different depth we have received the soil sample, and then after testing we should know this, we know these properties. So, at depth, every 1.5 meter depth the soil is collected, 1.5 meter, 3, 4.5, then you can see up to 12 meter. We have the up to 12 meter data, and these are the soil type. SP means poorly graded sand, and SM means silty sand, okay, and WS means well graded sand, okay. And as that, if I for different soil type and the grain size, if I discuss about that, then it is well known that for poorly graded sand is more susceptible in liquefaction as compared to the well graded sand. Okay, that means the well graded sand is less susceptible in liquefaction as compared to poorly graded sand. Similarly, for the rounded soil particles are more susceptible in liquefaction and as compared to the angular soil particles. Okay, so here the possibility of liquefaction is more for poorly graded soil or sand as compared to well graded, but again we have to check it and then we will find that. So, now for this is the your D50 value. What is D50? Then the percent finers, I mean the 50% soil particles are finer than this value. Okay, so that is D50 is 0.21, 0.2, 0.22, and for SM it is 0.15 to 1.14, and it is 0.25, 0.24 in terms of millimeter. Relative density that is required. So, this is 21%, 25, 32, 37, 42, 50, 55, 60. And water table is 2 meter below the ground level. Gamma sat is 20 kilonewton per meter cube. Gamma bulk is 18 kilonewton per meter cube. Gamma W is 10 kilonewton per meter cube. Okay. Gamma W is 10 kilonewton per meter cube. Okay, it's not 20, 10 kilonewton. And Amax is given, this is 0.2 G. Amax is given 0.2 G, 0.2 G, or Amax by G is equal to 0.2 with magnitude of earthquake is 7.5. In previous lecture also we are discussing about the magnitude. Those magnitudes all are moment magnitude. Okay. So, this is 0.2 G and this 10 kilonewton per meter cube. So, now we have to check every depth whether liquefaction will occur or not, but I will show you only two depths. So, I will check it for 4.5 and I will check it for 9 meter. Only 2, and the similar way you can check it for other depth, and then you will find that up to which depth the liquefaction will occur, or up to which zone the liquefaction will occur. Clear? So now, so let me first determine at depth 4.5 meter. Okay. So at 4.5 meter, D50 is equal to 0.22 millimeter, and RD is equal to 32%. You can see that at 4.5 meter, 0.22 millimeter, RD is 32%. Okay. Now our Amax by G is equal to 0.2 and MW is 7.5, and your gamma sat is equal to 20 kilonewton, 20 kilonewton per meter cube. Gamma W is equal to 10 kilonewton per meter cube. So gamma sub is equal to 20 minus 10, that will be 10 kilonewton per meter cube. Gamma bulk, that means the water unit weight of the soil above the water table, is 18 kilonewton per meter cube. Okay, so first I will calculate the tau average, that is the developed, that means the shear stress developed during an earthquake. What is the expression? That is 0.65, then your Amax by G into sigma V into RD. So first I will calculate the sigma V, or I can put the value here. So first, what is RD value? So I will use this table, this chart. What is RD value? It is 0.4 meter. It is 4 meter. So this is your 6 meter. So RD, this will be around here. 4 meter. This value is, this is 0.9, 0.96. This is 0.4 meter. The average value. This is 0.96. Okay. So this is 0.96. This is 0.9. So you can see here it is around 0.96. So I can write that this is 0.65 into Amax by G is 0.2 and sigma V, it is total, it is not effective. Total will be below, above the water table 2 meter, because water table is at 2 meter below the ground surface. Then it is 20 into 2.5, okay, into 0.96, the RD value. So 0.65, 0.2 sigma V into 0.96. So that is coming out to be your 10.73 kilonewton per meter square. This is the shear stress developed during the earthquake. Which earthquake? The design earthquake is, the earthquake is taking with a magnitude of 7.5 with Amax by G is equal to 0.2. Okay. So now I will calculate the shear stress required to cause the liquefaction. Tau H sigma B dash. And for this is related density equal to 32%. So that is equal to your triaxial data I will use here, half sigma D by sigma 3 dash. So triaxial, that is for RD 50%. Why 50%? Because later on you will use the chart where the chart is developed, charts are developed only for RD is equal to 50%. So that is into relative density is 32 divided by RD value 50%. So now here your MW is 7.5. So MW is equal to 7.5. And what will be the uniform number of stress cycle? This we are using this simplified procedure. What will be the uniform number of stress cycle? That will be here we will consider 20. So that is given, I have discussed in my previous class. So that will be 20. So now how I will calculate CR and how I will calculate this value, half sigma D by sigma 3 dash. Now CR I will get from here. What is my relative density is 32%. So 32% CR, your CR value is, this is for beta, CR will I have to go from this side. So if I extend it, this is 0.55, this will be around 0.56. Okay. So this value will be around, the CR value is if I extend this one, so this will be around 0.55 or 54, or so this is, if I extend this is 0.5, this is 0.55. So this is will be 0.54. This is 0.55, this is 0.6, so this will be 0.54. And how I will get this value? So that means CR is 0.54 from the chart, 0.54. Okay. Now half sigma D, to use that I will use these two chart. Those are developed by Seed and Idris in 1971. So you can see, so first chart is developed for number of stress cycle 10. Second chart is developed for number of stress cycle 30. Our is 20. So I will take 10 one and 21, then I will take the average value. 10 1 and 31, and then I will take the average value. Because our case the uniform stress cycle we have considered is 20. So but here the charts are available for 10 and 30. So if I take these two and take the average value, then I will get the uniform stress cycle for 20. So now here this is my this is half sigma D by this is half sigma D by half sigma D divided by sigma 3. Okay, this is half sigma D divided by sigma 3, or you can write sigma 3 dash also. Okay, same thing. So that means here if it is effective, then it will be sigma 3 dash. So now I will get this is mean grain size distribution. This is D50 is how much? D50 is 0.22. So it is 0.22. This is 0.1. This is 0.22. So corresponding value will be around 0.22. So this is 0.1, 0.3. This is 1.3, 0.1. So this is in log scale. Okay. So that's why I can get, so this value is around 0.22 will be here. Okay. And this value will be around here 0.22. Okay. Similarly for here 0.22 will be here. So this value will be around 0.18, 0.175. So this is 0.17. This is 0.175. This value will be 0.175 here. Because if you go here, then this value will be around 0.22. Yeah. So this is less. So this is the value corresponding to here. So this is around 0.22. Okay, so you will get the value from the chart. Okay, so when you are taking the value from the chart, so there may be slight deviation, that is acceptable. Okay, so this deviation, slight deviation is acceptable because we are taking the value from the chart. So what I have taken that for n equal to 10, that is half sigma d by sigma 3 or sigma 3 dash, that is equal to 0.22. Now for n equal to 30, that half sigma d by sigma 3 dash, that is equal to 0.175. Okay, so this is actually, this axis is half sigma d by sigma 3. This is mean grain size distribution. This is for stress cycle 10. This is for 30. This is for n is equal to 30. This is for n is equal to 10. Okay, and here I will get, if I know the d50 value, for 30 I will get the half sigma d by sigma 3, and here for n equal to 10 I will get the half sigma d divided by sigma 3. Okay, so now for n equal to 20, I am taking the average value, half sigma d divided by sigma 3 dash. So I am taking the average of these two, 0.22 plus 0.175, which is equal to 0.1975. So now this is also known, so now I will put it here, 0.1975, then this is 32 divided by 50. Okay, so this value is 0.068256. Okay, so now sigma v dash, now it is sigma v dash is what? Effective overburden pressure plus sorry, this is 20 minus 10 that I have already shown into 2.5. So this will be 61 kilonewton per meter square. So tau A will be equal to, that is required to cause liquefaction or liquefaction resistance or resistance test, we can say. So that is equal to 61 into 0.068256. So that is equal to your 4.164 kilonewton per meter square. So you can see the tau average developed is greater than tau A. So liquefaction will occur. Okay, so or you can get the factor of safety also, that is nothing but your tau H, which is resistance or the requirement, divided by tau average, which is 4.164 divided by your 10.73. So this is 0.39. So obviously which is also less than 1. So liquefaction will occur. Clear? Now I will do it for another depth. So that is your depth 9 meter. Here D50 is 0.14 millimeter and relative density is 50%. Okay. Now I will calculate the tau average here. Here again 0.65 A max by G into sigma V RD. What is the RD value? Again you calculate. RD is now it is 9 meter, which is here. So RD will be around 0.89. So RD will be around 0.89. This is 9 meter around. So RD is 0.89 for these two cases that I have considered. So that RD is 0.89. So it is 0.65 into 0.2 max by G. Okay. Then the sigma V will be 18 plus into 2 plus 29 meter into 7. 9 meter into 0.89. Okay, so this is equal to 0.65 into 0.2 into 18 into 2 plus 20 into 7 into 0.89. 89 is the RD value. So I will get the value as 20.36 kilonewton per meter square. Now I will calculate the tau H divided by sigma V bar for RD is equal to 50%. So here CR value will be how much? Now here my relative density is 50. So this is 50. So CR value is 0.57. This is 0.55, 56, 57 around 0.57. Okay. So I am taking CR value is as this is your CR half sigma D by sigma 3 dash into triaxial, that is your RD is equal to 50%, and charts are also developed for 50%. So this is 50 by 50 and CR is 0.57. Now RD value similar way I can calculate the half sigma D by sigma 3 from the chart, and it is for n is equal to 10, that half sigma D by sigma 3 dash from the chart is equal to 0.225, and for n is equal to 30. For n is equal to 30, I will get sigma D divided by sigma 3 dash from the chart is equal to 0.18. Okay, initially it was 22, now there's a slight increase, that is 0.225, and this is 0.18. So for n is equal to 20, that half sigma D by sigma 3 dash, that is equal to half 0.225 plus 0.18. So that is equal to 0.2025. So now I can write here 0.2025, and that this one is again into 1 because both are same. Because you can see those charts are developed for relative density 50 only. So relative density 50 only. You can see this chart is developed for relative density 50 only. Okay, that's why we have to use this relative density correction. Okay, so now it is equal to, we'll get this value is 0.1154. Okay, so this is 0.1154. Now sigma V dash is equal to 18.2 plus 10 into 7. So this will be 106 kilonewton per meter square. Okay, this is 106 kilonewton per meter square. So tau h, that will be 106 into 0.1154, that will be equal to 12.23 kilonewton per meter square. So here again tau AV is greater than tau H, so liquefaction will occur. Or again, if I calculate the factor of safety, it will be tau H divided by tau AV, then this will be equal to tau H is how much? Tau H is 12.23 and this is 20.36. So this is 0.6, still it is less than 1. Or if you provide some factor of safety for liquefaction, then that you have to consider. Now I am taking, if factor of safety is less than 1, the liquefaction will occur. Okay, so you can see that as your depth increases, the factor of safety increases. Okay, so I mean this way you have to do this checking for the depth up to which you have that sand layer, or up to which you have that influence zone of your foundation. Then you have to check whether liquefaction will occur or not. If the liquefaction will occur, up to which depth. Then you identify up to that the zone of liquefaction or that depth of liquefaction. Clear? So we have here data up to 12 meter, I think. Yeah, 12 meter depth. So we can check for every depth up to which liquefaction will occur. And if you have the more data, you can go up to say 15 meter, 20 meter also, and then you can check the up to which depth the liquefaction will occur. So, but this check that I have discussed is based on the this is based on the laboratory test data. But the laboratory test data, this laboratory test, there is some limitations, So because here everything is given in terms of relative density only. You can see it is relative density only. So if you know the relative density, you can get this value. But in the actual field condition, this liquefaction is not only the function of relative density. So it is better to use the field test data to check the liquefaction susceptibility of the soil, or the liquefaction will occur or not. And so next part that I will discuss is that your evaluation of liquefaction resistance of soil use field test data. Again here I am saying that I am concentrating on the sandy soil or coarse grain cohesionless soil. Okay, later I will discuss about the fine grain soil also. Okay, so now evaluation of liquefaction resistance was use the field test data, and this is the most acceptable methods to know whether liquefaction will occur or not, or evaluation of liquefaction resistance of soil. And now the method that I will discuss, that is available in this literature. You will get the liquefaction resistance of soil. The summary report from two workshops. One is in 1996, one is 1998, and it is available in Journal of Geotechnical and Environmental Engineering, ASC. So you will get for this reference also you will get, and you will if you get, you will get more other information also. So, and this the similar or the same procedure is recommended by IS code also. This is IS 1893 part 1 to 2016. So that also recommend the same or similar procedure. So that is recommended, even not only in India, then worldwide these methods are being used to know whether the liquefaction will occur or not. So that's why here these two terms are used. Where is the CSR or CRR? Okay. Now, what is CSR? CSR is called the cyclic stress ratio that I have already discussed, which is the actually the your that now this initially I discussed the CSR, the cyclic stress ratio, that is for the your stress required to cause the liquefaction or the resistance. So initially the both were represented by CSR. I mean cyclic stress ratio, which is for resistance ratio, or the cyclic stress ratio. But now it is CSR is basically the cyclic stress ratio, which is the your tau AV divided by sigma V bar. So sometimes, as I mentioned, you can write sigma V dash also. So that means now remember that now here my CSR is actually tau AV divided by sigma V dash, and CRR, cyclic resistance ratio, that is tau H divided by sigma V bar. Clear? But in my previous simplified method or the lab test, there I represented CSR by tau H divided by sigma V dash. But initially both the things were represented by CSR, cyclic stress ratio. One is developed, another is required, or resistance. But now it is represented in CSR means the stress developed during earthquake, that is cyclic stress ratio, and CRR is the cyclic resistance ratio, which is the stress required to cause liquefaction or the resistance stress, I should say. Okay. So now remember that, don't be confused. Okay. Initial also that CSR we wrote TH divided by sigma V bar. Okay, for simple shear. Now I am writing CRR. Okay, so now this method I will use the CSR is the stress developed during a earthquake, and CRR is the stress required to cause an earthquake. So my factor of safety will be obviously resistance, that means CRR divided by CSR, which is the same as tau H divided by tau AV that we are following. Now that CRR means is tau H is divided by sigma V dash, and CSR also TAV is divided by sigma V dash. So these two ratios. Okay. So you can see this is your cyclic resistance ratio, and this is cyclic stress ratio. So now cyclic stress ratio is the same as I have discussed in the laboratory test procedure case, which is same, that is 0.65 Amax by G, and there was only sigma V. Here now it is normalized by sigma V dash, so it is sigma V dash into RD. Okay. So now here, as I mentioned, that it will be sigma V dash, or it can be sigma V bar, or it can be sigma V 0 dash. The 0 means the initial. Okay, or sigma V 0 dash. So all are same. Okay, I may use different notations at different times. So because they are representing the same thing. That means initial effective overburden pressure. Clear? Now, where the Amax is the peak horizontal acceleration or PHA. Okay, I will discuss that how we will determine the PHA or Amax, that I have already discussed in my previous module. Okay, but you have to very careful when you use the PHA or Amax, that whether those datas are the ground surface acceleration or not, because as you know, we have during the derivation of CSR or tau AV, I have discussed that this is applied at the ground surface. Amax is applied at the ground surface. If it is at the bedrock Amax, then you have to do the ground response analysis, and from the bedrock you have to get the ground surface Amax, that you have to use. Clear? And for bedrock also Amax, how you will get that, we have discussed different attenuation relationships. So that means from there you will get those data, or for your for particular site you can go for seismic hazard analysis also, and from there you will get the Amax. Okay, if it is ground surface Amax, then you can directly use, or if it is the bedrock, then you have to do the ground response analysis. From the bedrock you will have to get the ground surface acceleration Amax, and that Amax you have to use here. Okay, so those I have already discussed in my previous module. So now here Amax is the peak horizontal acceleration at the ground surface generated by earthquake. Sigma V or sigma V dash and sigma V0 or sigma V0 dash are the total and effective vertical overburden stress respectively. RD is the stress reduction coefficient. Now in the previous case, this is the same chart that is given by Seed and Idris in 1971, but here in the previous case we use the chart. Here this average line expression is given. So what is the RD expression? RD expression is this one, if Z is less than equal to 9.15 meter, and RD expression, so you can see there is two parts. This is the equation 2, this is equation 1. It is up to 9.15, that means up to this portion is equation 1 and this portion is equation 2. This is equation 1, this is equation 2. You can see which was equation 1, this is my equation 1, this is equation 2. And for 9.15 meter to 23 meter, this is the equation RD. So now, if as I have already mentioned that when you are taking some value from the graph, so there is a possibility of there is a marginal difference. If it may vary to person, okay, it may vary for person to person. So that's why if we have the equation, then it is very difficult to use, easier to use that equation. So then you will get only one particular value if you have used the equation. So always it is better to use the equation rather than using the chart, because, and that's why this equation is developed. And so equation of RD or equations for RD is developed for two different zones. So one for 0 to 9.15, that is the equation 1, and from 9.15 meter to 23 meter, that is equation 2. So from there you will get the RD, and Mx by G 0.65, Y here 0.65 is applied. So we know all these things, that is already been discussed. And this is sigma V or sigma V dash, you know how to determine that for a particular day. So this way you will get the CSR cyclic stress ratio, which is basically the T average. Now here this is two equation is been proposed, but here only by a single equation we can represent that average line of this graph by single equation, that is Z is depth below the ground surface in meter. We can use these equations. So in my problems I will use these two equations when I will solve the problems, but both two types of equations are available in two zones and one single equation. So this way I will get the stress developed during an earthquake, or CSR, cyclic stress ratio. So in the next class I will discuss that how I will determine the stress required to cause the liquefaction, or the resistance stress, or the here it is given the cyclic resistance ratio. So that means you understand these things, that the cyclic stress ratio, that means the stress developed during an earthquake, is same whether you use the field test data or lab test data. That method is same. Even if in the lab test whether you use the cyclic triaxial data or simple shear data doesn't matter, the CSR value or the tau average, that expression is same. Even if in the lab, when I will discuss about the different method to determine the CRR, cyclic stress ratio, okay, or cyclic resistance ratio, CRR, then you will find I will use the CPT, I will use the SPT, I will use the VS value to determine the CRR. But whatever, there are different methods are available, different test methodology, whether field or lab, because as now you know that field test or field methodology are more preferable or recommended over the lab methods to check whether liquefaction will occur or not. Okay, so that for liquefaction, evolution of liquefaction resistance of soil, field method is more recommended. Okay, so that you know, so for there we will use the different methods. Okay, that CRR determination methods, different methods or test methodology are available, but for CRR or tau average, there is only one simplified procedure that we will use. Okay, so in the next class we will discuss that. In this class we will discuss how we will get the CSR or tau average. Even for the field test it is same, but only difference in the lab we use the graph to determine or calculate the RD. Here we will use the equation. Those are available. Now in the next class I will discuss how the different test methodology can be used to determine the CRR. I will discuss mainly three test methodologies, that is the use of SPT or the standard penetration test, CPT, static cone penetration, or SCPT, the cone penetration test or static cone penetration test, and use of VS data and the shear wave velocity data. So most of the time it is very common to use that SPT and CPT for evaluation of liquefaction resistance of soil. I am talking about again the coarse grain sandy soil. Okay, so soil, but sometimes VS is also used, velocity of shear wave is also used to do that. Okay, so these three methods are very popular. That's why I will discuss these three methods in the next class. Thank you.